for people who were asking on how to access the labs, you should have received an email with a code that's QU Summer School. So when you go in and go to qu.academy and go to register, just put in your information, and in the registration code, type in QU Summer School. And once you do that and you sign in, you'll see a screen which looks like this. Filter to the courses Q Speaker Series. You'll also be able to get the code from Tony Guaida's talk from last week. So he shared his book's code for all the factor investing code. So you should be able to access that. And so this is today's presentation. So you click on more details, and then you will be able to see all the slides. Can you hear me? Okay, so you'll be able to see all the slides and the video of today's presentation. And I will work with Paul to see if we can get another video for just the presentation, for Paul's presentation, and add it to this particular site. But to access the labs, Matthew was mentioning, so you just need to click on this Run on Q Sandbox. And when you do that, you're going to see this play button, and you should be able to see the 4 files. So that actually has both the files, the reinforcement learning and the inverse reinforcement learning files, which Igor was mentioning. That's 3 and 4, and 1 and 2 are the interpretability and the de facto model files. So I've just integrated. There are a bunch of ways in which we could have integrated. Just because these were 4 files, we just tried it on Google Colab and it worked. So I've just made it available through Google Colab. So anybody with the Gmail access should be able to access these. And the one thing I really liked was I go into runtime, especially if you're using deep learning, change runtime, and then use GPUs. That way it's going to be much faster. And you should be able to access all the code and associated labs. For Tony's presentation, we actually had to embed them in a different way, but that's as simple as that. So you should be able to access all the code which Matthew was sharing. And I think Matthew also shared his GitHub link. So if you want to set up your own sandbox with Conda and all the required files, you should be able to do that there too. So I just wanted to take a minute to help everybody understand how to access the files. And when you get an email afterwards, you will have the same instructions. So you should be able to try it out of the lab. So it's 12:35. How about we jump to the fireside chat session? I know a lot of questions are coming in. So I have some questions too. This was an excellent presentation. And thank you so much for making the time to present today. So I usually do this. It's just to kind of set the mood for our fireside. I got a fireside background with the real fire in the background. So it works well for the fall season with an apple cider, hot apple cider, I guess. But we'll kind of set the mood. And for today's, I think we are getting some questions on the YouTube streaming channel too. So I'm going to consolidate some of the questions we get there and also some of the questions we have been receiving on Zoom. So we have a question on rigorous outlier elimination and then switching to a simpler. So can we perform a more rigorous outlier elimination and then switch to a simpler statistical model than a lot more complex neural network? This way we can deal with downside risk without compromising model complexity. Any thoughts on that? It's a modeling technique question. Should we go ask a neural network to capture all the idiosyncrasies in the data we are seeing, or maybe just eliminate outliers, build a simpler model, and then augment it for if-then-else kinds of conditions?
Yeah, so I mean, I'll take this. So I think there's the first way of answering this question, and that's around the bias-variance trade-off. And so with the bias-variance trade-off, as I'm sure you know, there is a question of how much regularization or auto shrinkage you need so that you are essentially not overfitting on the in-sample data, and you're trying to ensure sufficient or sort of minimum variance so that the performance in sample has a little bit of bias, but it actually does better. It does, it doesn't perform nearly so worse out of sample. So that's the bias variance trade-off, where you introduce some bias in the hope of capturing better out of sample performance, less deterioration in the in-sample and sample performance. So that's one way of thinking about this kind of problem. Now, I think the answer about capturing outliers is very much an application-driven type of decision. And if you go back to the factor modeling examples, if you compare the mean squared error between linear models, lasso, and deep learning, there's really little of a story there. All the interesting content is in the tail regions of the distributions. Mm-hmm. And so that's actually a slightly different problem from the bias variance trade-off. There, what you're trying to do is you're trying to actually try to, to capture these, or at least measure how well you're capturing. And the idea is not to throw that information away, but to try and capture as much of that as possible. And we use just simple mean squared error fitting, but you could, of course, use different types of techniques for fitting if you really want to maximize how many outliers are being captured. So I would say non-linearity is really the question. Do you really want non-linearity in your application? And if so, to what extent are you trying to pick up on sampling error versus pick up on actual sort of the signal? And of course, you won't really know anything until you construct what are called learning curves. And learning curves give the ability to understand, with the increasing number of samples, how does the variance look? In other words, how many samples do you need in the data? If you have the luxury of having that enough data, how many samples do you need in order to reduce the variance? So that's another problem as well we didn't discuss in the talk.
Absolutely, yeah. Thank you, Matthew. I think there are a couple of questions for Igor. I see like 2 questions on the YouTube channel and also a couple of questions in here. So I'll try and consolidate a couple of them. So one question, a specific question is, how can you model probability of trade execution? And could you use reinforcement learning or inverse reinforcement learning for this kind of a problem? That was one of the questions, Igor.
Yeah, so the difference between reinforcement learning and inverse reinforcement learning, as I mentioned in my part, is what you know, what you assume to know about the reward, which is actually maximized by an agent. So I think the setting which is most suitable for optimal execution is direct reinforcement learning. But this assumes that you know what the reward or objective function that the trader is maximizing, and usually what is maximized in optimal execution is some sort of balance between the slippage and the risk of the remaining inventory, right? So it's kind of similar to the mean variance optimization in the classical portfolio setting. This is one possible approach to optimal execution problem. So if you believe in applicability and relevance of your reward function, then the reinforcement learning would be the right approach. Now, if you have historical data obtained while exercising some execution strategy, and you want to make the reverse engineering of what actually was the objective function of the agent, then you would be better using inverse reinforcement learning.
Mm-hmm. Okay, good. And I think there was another follow-on question, similar to the cart pole problem we all familiar with. Are there any specific financial data sets you would advocate for trying out reinforcement learning problems in finance? Is
the implication real world data sets?
I think the question is just to try out reinforcement learning in the financial services setting. Are there like cart pole like problems which you can use for benchmarking different kinds of algorithms?
Yes, the answer is yes. And one kind of cart pole problem is exactly what I presented in my talk, right? The other cart pole type problem is actually the most classical problem of option pricing, which is pricing the European option, put or call option. So we have a chapter in the book which outlines this model that we call QLBS, which stands for Q-learning for Black-Scholes problem, which actually does exactly that. So you can simulate your data, right? You know exactly what you do. You know exactly the model from which you simulated, and you even know the answer. The answer in some of the limiting cases will be given by the Black-Scholes formula. So you can benchmark in a completely controllable setting. So it's exactly carpal type of problem.
Okay. Yeah, and I'll just add to Igor's comment as well that for AI Gym specifically, there are a couple of options. There is an optimal execution problem for market making, which we have in the book, and it's also one of the notebooks that sets it up. It actually uses a sort of derivative of AI Gym called T-Gym, Trade Gym, okay, which is built off AI Gym. And also we have the financial cliff walking example as an AI Gym export. It's not in the repository, but we're happy to share that too. So that's just a note about code.
Nice, nice. So those would be excellent examples just to kind of try out in a financial services setting. So Paul, I actually had a question. I know we didn't get to the actual applications. So when we talk about MCMC in the context of finance, like what asset classes or like which kinds of examples would you typically use these kinds of algorithms?
So here is an example. Can you guys hear me okay now?
Yes.
So here is an example. So you have a stochastic volatility model, right? So the evolution of your spot will be your observation process. The stochastic volatility itself will be the latent state. So we want to understand the latent state given the observed, for example, market prices, right? So we want to back out the stochastic volatility process. So this can be done in different ways. This can be done using, for example, the frequentist estimation, where you run a particle filter. That's one estimation of your maximum likelihood, and then you basically maximize the maximum likelihood, and you back out the parameters of the stochastic volatility model. But the second way to do it, the Bayesian way to do it, would be to use Markov chain Monte Carlo, and there are notebooks in the examples that you can look at. Those where we use I believe we use PyStan and or PyMC3, and you can look at how that is basically done in the examples.
Very interesting. Thank you. I actually had a couple of other questions, and these are probably more, I would say, general compared to that of the specific questions which are associated with the lectures. I mean, in the summer school, in the last few months, we have had a diverse group of people who have attended the various sessions in summer school. Some of them come from a regulatory perspective. They're working as regulators, and they're kind of figuring out how should AI and machine learning be regulated. And on the other hand, you have asset managers who are looking for potential trading strategies or applications of AI and machine learning for trading and wealth management and portfolio management kinds of applications. On the other hand, obviously, there are people who are interested in just the trading aspect of it and looking at historical data and potentially building out models. Now, though there are so many options in terms of modeling possibilities, we haven't really seen established best practices in the context of machine learning wherein everybody vouches by these techniques as the method. So if there were success stories in your perspective, rather than just approaches which are potentially being advocated, what are those success stories? I know many quants don't like to talk about it if it's successful, but what are the success stories of machine learning which people have to think about? If they're not using it, they're being left out, kind of a thing. So it can maybe it's an open question for all of you. So you can maybe each take a turn and talk about those based on your background.
Yeah, I'll jump in and then let Igor and Paul elaborate just very quickly. So in the book, we do actually discuss in chapter 1, the problem of, why or to what extent, and what are the challenges, the barriers to adoption. There's actually a separate paper that just came out with Igor and I called the 4 Horsemen of Machine Learning and Finance, that discusses some of the more conceptual problems. It's not a straight shoot. Now, in terms of the top applications, I think Igor can speak to his QRBS model for hedging. I've certainly myself, I can provide a testament to asset management firms working on the factor models, deep learning, and I would say, of course, within trading, optimal execution, reinforcement learning. Those are definitely being used across banks and trading firms, Chicago, New York, elsewhere. So I'll defer to Igor and Paul for specifics in the areas that they've worked, but just to mention that those are discussed in the book.
Cool. So Paul, Igor, you want to take a stab at the question?
Our industry is not very open, as we know, right? So people don't talk much about specific things that they do, and I'm not exception either. So I'm not clear to talk specifically about what I do at Fidelity, right? But as Matthew mentioned, in my area of coverage, reinforcement learning. Definitely, there've been lots of interest recently because there've been rumors. I've heard some rumors that some trading shops were very successful in using reinforcement learning for trading. My own focus is actually rather on inverse reinforcement learning. That's my favorite topic. Not much is published there on this thing. I hope to be able to report some success maybe on some future events after I'm cleared for this, right? But the other thing, like again, it's a little bit subjective what we call success stories, right? So we can differentiate between like stories when you. I don't think we have examples when you just cannot proceed without using machine learning in quant finance, right? So always we have something else, right? So always the question is like, what is the criteria of success? So to me, one of the criteria of success is a conceptual clarity of what we do, right? And how we put, classical quantitative finance in more general framework. How we can take a look at this from outside. How we can connect, like, for example, given this example that I mentioned of Black-Scholes model, right? How exactly Black-Scholes model connects to machine learning? If you look at the Black-Scholes equation, there is no connection at all.
Right.
It's not on its own, it's not optimization problem, right? It's some sort of a differential equation which gives you one number, which is the price, which is the fair price. And some people, some practitioners whom I know, are very critical of this whole concept at all, because they say, well, it misses half of the answer. It misses the whole range of questions about the risk of mishedging risk, right? So the classical model doesn't tell you anything about that, right? And it's a very severe drawback in my view, right? So when you look at these things from another perspective, from the perspective of machine learning, then you do see the connection. And the connection is actually very simple. As long as you stay with discrete time, dynamic formulation, dynamic programming formulation, then you clearly see all the elements of machine learning. And that's exactly what we explained in the book, right? So, and then it's very obvious what is the problem that you're trying to solve. You're trying to solve the problem of reinforcement learning, of maximizing some sort of risk-adjusted return, if you wish, right? And then once you understand that, then you can establish links with the classical finance. Then you can find, okay, what are the circumstances under which the classical finance works well? We know them, right? So the market should be liquid, et cetera, et cetera, et cetera. We just don't know how to quantify them, right? What are the criteria? What is the requirement? How liquid they should be? What are the criteria? How frequent should be your rehedging, et cetera, right? So to me, like, this is a very important part of the whole thing, right? Not, boasting like P&L numbers, this number versus another one, but rather understanding like how it all fits into one unifying picture.
Absolutely, absolutely. And we had a few weeks back, we had Dr. Agus Sargento from Wells Fargo. So he kind of presented similar thoughts. And I think he was coming more from the perspective of model risk, especially for
Yes.
machine learning models. And one of the themes in the summer school we are doing is we have had a one track with 8 weeks of machine learning. So we're kind of looking at each one of the themes and slicing and dicing, understanding the evaluation criteria, the algorithm specifics, the structuring of the problem type of thing. On the other stream, we are focusing primarily on how do you think about model risk for machine learning models? How do you validate a machine learning model? How do you think about evaluating stress tests and scenario tests and edge cases for machine learning models? I know, Matthew, you had a couple of comments on the interpretability side of things, primarily for deep learning models. Now, I've also been looking at the whole notion of explainability, which people talk about, various ways in which you could, irrespective of the model you've used, will be able to try and explain the results or do other things. So what are your thoughts in general, if a company is either adopting machine learning or considering adopting machine learning, how should they be looking at model risk in general? Because it's a novel area, and while people are excited about the promise of machine learning, but there are also these hidden risks which we haven't even discussed and quantified or even brought to the surface yet. And what does it mean from a fiduciary perspective? So your thoughts on that? I can just open up the floor, and maybe Paul, you can go first, and then Matthew and Igor, you can probably chime in.
I think in terms of model risk, the entire framework of cross-validation, I think, is of critical importance. It's being able to assess the performance of the model out of sample. And when looking at the out of sample performance of the model, it's also about making sure that you're looking at the right metric. So when you asked where a lot of success is currently concentrated in machine learning, there is a group of organizations called the algorithmic market makers. Many of them are non-bank algorithmic market makers, such as XTX, for example. And they have been using machine learning very, very successfully to trade in a very, very competitive environment. And they have, I think, very, very interesting approaches to validating their models, which they have to do because their profitability depends on that.
So in our book, we actually, in chapter 1, we actually look at a sort of a mini use case in mortgage modeling. And that actually, the 2008 financial crisis is very much, in a sort of a sobering reminder of where things can go very badly wrong for modeling. So, I mean, I worked as a quant at Lehman, structured credit, right in the heart of the credit world. No one really saw the crisis coming, or very few. And if you look at the example, we look at a mortgage model which tries to predict out 10 years, but it has siloed data gathering in it. It was based on a few variables, mainly based on sort of intuition, one-dimensional sort of hand waving and trends. And really the reality of a lot of modeling variables is that you need to have a much more general data capturing process, capturing alternative data, avoiding sort of bias, human bias in that data capturing, and also allowing for the fact that there are going to be, you're not going to be able to visualize a lot of the effects, the interaction effects, non-linearity. So I think machine learning addresses the problem of ultimately sort of weaning us away from, as Paul mentioned, both in-sample performance and also from this sort of very narrow data silo and sort of very sort of human-centric way of selecting models like FICO score, for example. And instead opens us up to this vast array of possibilities for how you configure models. It doesn't limit us in terms of non-linearity, and it also puts the outer sample performance there. And I think there's a whole host of issues to discuss we don't have time to get into, but broadly separating them out, and I think Marcus Lopez de Prado does this very well, is he discusses at a sort of meta level where machine learning is going in the finance industry, whereas we get down much more into sort of the modeling issues, the model risk issue at the model level. And so, anyone wondering, why should I read this book when you read Marcus's book? Well, we really drop down into sort of, the specifics of very, well written, sort of worn trodden models, and what the specific model risks are within those ones. And that sort of becomes mathematical in its exposition.
Absolutely. Absolutely. Igor, you want to add any?
Yes. Thank you, Shri, for asking this question. The whole topic of model risk is very close actually to my heart, because my first job at JP Morgan before I became a desk quant was in the model validation group, and I was thinking a lot about model risk. Right, and this is a very, very deep and very important topic. I was horrified, for example, like Matthew mentioned, structured credit. And when I did a model review, I was looking into very scary beasts called CDO squared, which is CDO of CDO. And I was like horrified how much difference you can get when you switch from one copula model to another one, right? And what to do about that, right? So this is model risk. I think like it's a very, very multi-faceted, multi-dimensional question, right? So clearly, there is no unique answer to this, and there are lots of, practical limitations. For example, one simple-minded approach to kind of get a sense of model risk is just to implement few different models, right? But it's not always practical, right? It's not always available, right? So I think machine learning, what additional views, insights that can be brought by machine learning are pretty much related to the flexibility of machine learning, right? So we can easily tweak, architecture in let's say some generative models. So for example, like people work with market simulators. I have different set of arguments, pro and cons of using that for pricing, but certainly for as a measure, as a kind of tool to get a sense of model risk. I think it's very valuable, because you can easily tweak a little bit setting in your generative model, and then you get different dynamics, right? So it can emphasize the importance of tail events, etc., right? So it definitely gives you kind of better view what you can expect if you tweak your model a little bit, right? So and because all things here are highly nonlinear, very often very small tweak in the model can produce huge differences, as in this example that I mentioned of CDO squared, right? So, but my view is that the right approach to controlling model risk is a combination of relying on first principles of econometrics, of like how we should start with the right foundations, right? So we definitely should not have models which contradict general principles, which contradicts econometrics, which contradict physics, right? But in addition to that, it's not enough, clearly, right? But in addition to that, the additional insights of reinforcement learning are exactly this flexibility. So you can massage model, you can look at this from different perspectives. You can look at limiting cases when, like, everything becomes linear, so you can analyze it. You can consider, like in physics, there is a very powerful approach of looking at things analytically and look at the different limits, right? How the model behaves when you take this parameter to 0 or to infinity. Does it make sense or not? And sometimes you do this simple exercise and you find something like totally meaningless. And then you say, oh, okay, then I know that my framework is work. So I have to come back and redo this part. Right?
Absolutely.
It's a very exciting field. I was even thinking about some point about using Vapnik's support vector machine to measure model risk. It didn't go anywhere because I was distracted by some other things, but it's very interesting.
Yeah, let's pick it up as a follow-on project after this call.
Yes.
We're allowed to kind of collaborate on it.
Sure.
Actually, that's, you mentioned the market simulators. We in fact had a whole module on synthetic data generators and using GANs for generating WIX data as a part of the summer school for our students to just get a feel for, like, how do you kind of look at this whole notion of, if you're thinking about model risk and you do not have enough data and you want to kind of potentially try out alternative scenarios.
Yes.
So I think we are getting very close to 1 o'clock. We have a lot of a diverse group of engaged participants throughout the world who are attending these summer school series, and I'm very much appreciative of your time and your putting together all these amazing presentations and contributing to the community as a whole. One of the key goals of putting together this whole summer school was to bring in more discussion, openness, and transparency, and also engaging the thought leaders in the community to basically bring their work to the limelight, but also to make sure that we open up for discussion, because there are so many of these concepts which are novel, and many a times the proverbial black boxes which anybody wants to understand become something unreachable, and we really need to get into the black boxes to understand before we can even vet out whether it's appropriate for use cases. So I think contributing to those efforts through your rigorous research and writing a book is such a commitment and hard work, and I really commend you for putting all this time to put together this amazing piece of literature. Any last words before we end today's session for people who are either career transitioners who want to understand data science and machine learning? Obviously, I get a lot of questions. I mean, when I teach at Northeastern University in the business school and also in the engineering school, a lot of students, they come in the last semester and they say, what, shall I take that one data science course or introduction to Python course? That way I can claim myself to be a data scientist and join the industry. Obviously, there are so many things you need to understand, both from a finance perspective, the econometrics perspective, the optimization perspective, and now incorporating machine learning into bringing this holistic view of appropriateness of using certain kinds of models for certain kinds of situations. And that there is no I think Matthew, you were mentioning about the Kaggle thing. There is no set problem wherein you're just aiming for one metric to achieve, right? So how do you advise students? I know you're all academics, you're all kind of advising students. So how do you advise students who are or even career professionals who are trying to embark into this whole journey of machine learning? How do you encourage them, or what do you tell them as the best way to go about learning machine learning and applying it in their jobs? So maybe you can all have a few last minute comments before we adjourn for today.
Yeah, I'll just say something very quickly. So if you're a computer science or you've come from an engineering or hard science background and find this is new to you, a bit of advice that was given to me when I first joined is follow the money. Understand what drives the financial system, where the money is, because that's where machine learning will ultimately be sort of most heavily deployed, and your own salary, career trajectory and so on will depend upon that. So it's the first bit of advice. If you're on the finance side and you've worked in trading, quant, and you're trying to make the transition to machine learning, I would say that go back to your favorite sort of machine learning book, get sort of cleared up or sort of clued up on the math behind it, and then maybe pick up our book. I'm biased, obviously, but I would definitely recommend getting yourself plugged into as many resources as you can around programming, and realizing that it's a very fast-paced field, and that it's important to lock on to the most important high-level concepts and not get too caught up in all the toolkits. Okay, because that's just it becomes then just a massive sort of overload of information.
Absolutely. Paul, you want to add a few words?
I will say implement every model that you are interested in yourself, and start with the assumption that the model is rubbish, and try to disprove that, because a lot of people sort of start with this kind of blind faith in the model, and they basically start expecting magical results. So I think that, and without implementing this stuff themselves, they usually won't know any better.
Yeah, thank you. Igor, you want to have?
Yeah, I wanted to add to Matthew's recommendation that it's important, I think, not just follow the money, but also follow your heart, and do like what you really excited to do, right? And unfortunately, the quant finance is such a wild field that everyone with different, skill set and inclinations can find something very interesting and exciting to do, right? So you can focus on data side, you can focus on software engineering side, or you can do model building and focus more on math rather than on the implementation side. Yeah. That's one thing. So there's plenty of things to do for everyone, literally, right? The other general advice that I would give is also try to kind of come up with some sort of a top-down view of the world, right? So try to see the connections between different, let's say, different approaches in finance, right? So for example, like one example. Option pricing is often a thing which is taught on its own without relation to the portfolio management. But actually, one is the limiting case of another, right? So if you have a very simple portfolio which is made of a stock and cash, this is actually what is called replicating portfolio for the stock, right? So this immediately gives you connection between different things which are maybe like perceived first as not connected, right? So when I did physics, it helped me a lot, right? So when you start physics, you see so many things and you're lost, right? Oh, I have to learn this, oh, I have to read about that. And then it's like, eventually you end up with a mess, right? And only it takes time to, settle down and see, like, to find, like, for each item to find its own box in this system, right? To me, I think it's extremely helpful.
Thank you so much, Igor. Just to let everybody know, people who have registered, you're going to get an email and there's going to be a survey, and people who answer the survey, we're going to raffle a copy of Igor, Matthew, and Paul's book. And please provide your correct information. That way, if you are the winner of the raffle, we will mail the copy, the physical copy of the book, directly from Amazon to you. So thank you again, Paul, Igor, and Matthew, for spending our afternoon, your precious time and your afternoon with us, and hope to collaborate further and see how we can bring more clarity and more advancements into this field of machine learning in finance. Thank you again.
Thank you so much.
Yeah, thank you, Sri. Thank you, everyone.
Thank you. Bye-bye.